Salt, sodium chloride, rock salt, halite, table salt. Doesn't matter what you call it, it's one of the most commonly used chemicals on Earth. It has extremely low toxicity. An average person would have to consume about a pound of this material in one sitting for their life to be in jeopardy. Salt is easily obtainable. In fact, it's one of the most common ionic substances on Earth. Its abundance also makes it extremely affordable to purchase. In its unpurified state, it costs about $100 a ton. That's 5 cents per pound. Salt helps us to deal with winter snow and ice. As much as some of us love to slip and slide intentionally for fun, when it comes to travel, this can be an annoyance. It can cause delays and, in extreme cases, even lead to catastrophes. Now, if you're handy in the kitchen, you might have been told that throwing a bit of salt into a pan of water will cause it to boil faster or help your food cook faster. I'm sorry to say that this is actually a myth, but it is rooted in a bit of scientific truth. Adding salt to water does indeed change its boiling point. Certain biological systems can be reduced from their finely tuned states into total chaos by the addition of a little bit of ordinary table salt. Don't believe me? Just pour salt on a slug and then ask the slug what it thinks of the power of this simple chemical compound. When mixed with other common materials like vinegar, it creates an herbicide whose power rivals some of the most advanced chemicals that mankind has yet to devise for that purpose. Salt is so abundant, so inexpensive, and yet it is remarkably versatile and used in many applications. Is it just some happy coincidence that one of the most useful and used chemicals in the world is also one of the most inexpensive and abundant? Not quite. There's a reason why we rely so heavily on sodium chloride as a society. As indispensable as carefully designed, finely tuned chemical products can be, there are a few applications for which just about any material will do. In these cases, why not use the most abundant and affordable option? Why not indeed? During this lecture, we're going to consider solutions at extreme temperatures, both above and below the ordinary boiling and freezing points of water. So we have to very carefully choose the units of concentrations that we're going to use for our comparisons. You may remember that in our previous lecture covering concentrations of solutions, that we talked a little bit about different units of concentration and what makes them unique from one another. Today we're going to see exactly why we use one of those, the molality unit. And to start that, I'm going to have to talk first about molarity and why molarity isn't always the best choice. Consider 2 samples of solution. I'll put some solvent in there, we'll make it water. And I'm going to add the same exact number of moles of solute to each. So up to this point, these are identical solutions. But there's an important thing to consider here. Molarity is defined as the moles of solute divided by the number of liters of solution. And in situations where we're not varying temperature, that doesn't matter quite so much. But we're all pretty well aware that when you heat things, they tend to expand, and liquids are no exception to this rule. So my 2 identical solutions, when they're sitting on the bench next to one another, won't be identical if I heat one up. The molarity is going to change. By heating a solution and causing it to expand, I'm causing its volume to increase, which mathematically, as we can see here, causes its molarity to decrease. Well, now we're in a tricky situation because what happens if we're doing an experiment that involves a temperature change? Well, there's also a molarity change. So which molarity do I use? Which one's right? And the answer is neither one. We're going to use a different unit of concentration that doesn't change as drastically with temperature, if at all. What we're going to do is use molality instead. Let's repeat our experiment and consider how heating the solution will affect its molality. 2 solutions, identical amounts of solute. This time we're going to consider their molality though, and the denominator of our term is now kilograms of solvent. And we all know from experience that you can heat the object as much as you like. It's not going to change the mass. So even in the face of expansion, molality doesn't change. This allows us to use this concentration over the broad range of temperatures that we're going to need in order to discuss things like boiling and freezing in the same context. There are certain properties of solutions that don't depend on which solutes are present, only how much. Of course, the flavor of a wine, the color of a dye solution, or the cleaning power of a detergent depend absolutely on the identity of the solutes they contain. But some simpler, more fundamental properties, like the freezing and boiling points of solutions, are far less selective. We're going to focus in on freezing points, boiling points, vapor pressure, and a curious property of solutions called osmotic pressure. We call these colligative properties, named for the Latin term for bound together. We use this term because the properties in question depend not on the identity of the solute in solution, but only on the concentration of the solute particles dissolved. Isn't that amazing? That's right. When it comes to certain properties of dilute solutions, all that matters is the concentration of dissolved particles. They can be anything: molecules, atoms, or ions. We're almost ready to consider some of the colligative properties, but before we do that, we have to think about one more thing, and that is the effect of electrolytes on solutions. Recall that colligative properties depend only on the number of dissolved particles of solute, not necessarily on the identity of that solute. So what does that mean for electrolytes, things like sodium chloride that become ions when dissolved? Well, let's take a look. Let's consider this question. What's the molality of dissolved particles in a 1 molal solution of sodium chloride? Well, it's obviously 1 molal sodium chloride, but what happens if the sodium chloride itself dissociates and creates more particles? Oh, we have to account for that, don't we? So 1 molal sodium chloride is equal to how many molal of dissolved ions? Well, in this case, I've got moles of sodium chloride per kilogram of solution, and I'm after moles of dissolved particles per kilogram of solution. So where am I going to find the term that I need to place into this equation to affect the change on units that I desire? Of course, the stoichiometry for the dissociation of sodium chloride in aqueous solution. 1 mole of sodium chloride dissolves to produce 2 moles of ions. That's 2 moles of dissolved particles. So I can consider this to be a stoichiometric equivalence here. 1 mole of NaCl gives me 2 moles of particles, which means I can use that to make a conversion factor. That conversion factor is 2 moles of particles per mole of sodium chloride, set into the equation in such a way that units cancel and give me the correct set of units in my answer. I'm ready to run my calculation now, and I find that I have to treat this as though it were a 2 molal solution, even though it's actually a 1 molal solution of sodium chloride itself. We compensate for this term in many of the calculations we'll be looking at using something called the Van Hoff factor. And the Van Hoff factor is simply the ratio of dissolved particles that we get per mole of actual solute that we dissolve. And it can be estimated simply using the stoichiometry of dissociation like we did here. Let's see how some of these Van Hoff factors compare for different substances. Let's consider sodium chloride, which we've already done, and compare that to magnesium chloride, another common salt, or sugar. When sodium chloride dissolves, 2 moles of ions form, which means its estimated Van Hoff factor is simply 2. 1 for the sodium ion, 1 for the chloride ion. To estimate the Van Hoff factor for magnesium chloride, we have to acknowledge that we get 2 moles of chloride ions and 1 mole of magnesium ions, which means its estimated Van Hoff factor is actually going to be about 3. Whereas when I consider the dissolution of sugar, a molecule that does not ionize appreciably when it's dissolved, the Van Hoff factor is simply 1. It's the identity operator because there is no dissociation. The concentration of sugar is the concentration of dissolved particles. Now, armed with this knowledge, we can apply the correct Van Hoff factor to all the colligative properties and be sure that we're actually calculating them correctly. The first 2 colligative properties go hand in hand. They are the freezing point and the boiling point. It was long known that the freezing point of water decreased when salts were dissolved in it. In fact, you might remember from our earlier lecture on measurements that Daniel Gabriel Fahrenheit actually used the freezing point of brine, or salt water, as his reference point for 0 degrees on his now famous temperature scale. Fast forward to the modern era, where tons of rock salt are spread onto roads and sidewalks in the US alone every year to make travel safer by inducing melting. The use of rock salt relies on the phenomenon called freezing point depression. By interacting with the solvent through intermolecular forces, the salt ions interfere with the formation of the very specific interactions between water molecules that are needed to form a solid. The result of this is a solution with a lower freezing point than usual. Dissolved solutes also have an effect on boiling points of solutions. Imagine a solution in which sodium and chloride ions are present near the surface. These non-volatile solutes can't vaporize like water can, but they do occupy the solution near the surface, holding some of the solvent in a sphere of hydration, making it less likely to escape into the atmosphere and vaporize. So, the rule of thumb here is that more concentrated solutions prefer to remain liquids. Their freezing points are depressed and their boiling points are elevated. The extent to which these transition temperatures can change can be easily calculated if we know the constants governing those changes for the solvent in question. We call those constants the molal freezing point depression constant and the molal boiling point elevation constant. Now, let's see how we can use those constants. The freezing point depression that is experienced by any solution can be calculated using a generic equation. This equation. The change in freezing point is equal to the Van Hoff factor times a freezing point depression constant that is unique to that particular solvent times the molality of whatever it is that we've dissolved. So let's use that equation to answer this question. Sodium chloride solubility in water is about 6 molal. That's about as much as you can get dissolved in there. So let's assume that we've done that in an attempt to prevent water from freezing, for example, on the roads on a winter day here in the Washington, D.C. area. What is the freezing point of a completely saturated solution? What's the best possible depression I can expect? Well, to calculate that, I'm going to first calculate the difference. And the difference in the freezing point is my Van Hoff factor, which is 2, times the molal freezing point depression constant for water, which I'm going to get from a table, and that's negative 1.86 degrees C per molal. Finally, my molality, which is given to me by the problem as 6. This is my setup to solve this equation. So the change in freezing point, based on my calculation in degrees centigrade, is negative 22.3. Now I simply subtract that from the ordinary freezing point of the solvent, which in this case is 0 because it's water, leading to a freezing point depression of negative 22.3 degrees. That's almost down to 0 degrees Fahrenheit, and explains why sodium chloride, rock salt, is so commonly used in these kinds of applications, treating roads in the winters. Boiling point elevations behave very similarly. So let's do another calculation. Sodium chloride solubility, again, is 6 molal. What is the boiling point of an absolutely saturated solution of sodium chloride? We're going to use an equation that looks very familiar, doesn't it? Only this time it's the change in the boiling point temperature, and we're going to use a new constant called the molal boiling point elevation constant. But otherwise, it's the same type of equation. This is also a colligative property. So the change in boiling point will be determined by the Van Hoff factor, which is about 2 for sodium chloride, the boiling point elevation constant for water, which is plus 0.512 degrees C per molal, and of course the molality of the solution, in this case 6 molal, about as high as we can get it. So my unit analysis lets me know I'll get a change in degrees centigrade, and the calculation yields the result 6.14 degrees centigrade. But remember, that's the change. It has to be added back to the original boiling point of pure water, which is 100 degrees. So we arrive at a final boiling point of 106.14 degrees. Now, what this means is that if you're trying to raise the boiling point of water by throwing some salt into a pot of water that you're cooking with, you could saturate that salt. You could make absolute brine out of it, and it still would only boil about 6 degrees hotter. So there are better ways to accomplish that than adding that much sodium to your diet. So if boiling point is elevated by the presence of a solute, another way of saying that is that the vapor pressure of the solution is lowered over that of a pure solvent at any given temperature. The vapor pressure of solutions is indeed reduced when non-volatile solutes like sodium chloride are introduced. Just like boiling and freezing points, the change in vapor pressure is a simple function of concentration, although we have to use a slightly different unit of concentration to properly predict it. The vapor pressure of a solution will also change in response to dissolution of a solute. Let's figure out exactly how much that 6 mol solution of sodium chloride will change. The equation that we use for this is a little bit different. We don't use molality in this case. Instead, we rely on the mole fraction, but not the mole fraction of solute this time. This time we're worried about the mole fraction of the solvent itself. As that mole fraction decreases, so does the vapor pressure. And of course, that means that as concentration increases of the non-volatile solute, so does the vapor pressure. So let's apply this calculation here. The new vapor pressure exerted by a solution is equal to its mole fraction times the vapor pressure when the solvent is absolutely pure. So let's get this going here. We've got 6 moles of sodium chloride dissolved in a kilogram of water, molality. But molality is not important in this case. What is important is mole fraction, so I've got some work to do. Let's break this apart and figure out how many moles we've got of everything present. Now, remember, we're dealing with a colligative property, so we don't have the luxury of just using 6 moles of sodium chloride. We have to acknowledge the Van Hoff factor, right? That breaks down into 2 moles of particles. And our unit analysis in this case tells us the Van Hoff factor is all we need to get the number of moles of dissolved ions, courtesy of the NaCl that we put in there. A grand total of 12 moles in a kilogram of water. But how many moles are in that kilogram of water? Well, for that, we have to get the moles of water using the density. And in this case, I've used slightly unusual units for density. I've gone with kilograms of water and moles instead of grams. But I've compensated for that. And the reason I've done that is that I want kilograms to cancel out. So if I use 1,000 moles per 18 kilograms of water, I get the units that I want in my answer. My answer here is 55.6 moles of water. Now, how do we use this to determine the mole fraction of solvent in the new solution? Well, we simply place them into what we know to be the mole fraction calculation. Moles of solvent over total moles. That's going to be 55.6 moles for water divided by a grand total of 67.6 moles for both solute and solvent. This gives me a mole fraction of 0.822 for the solvent itself. Now let's use that mole fraction to complete the calculation. The new partial pressure of my solution, or vapor pressure of my solution, is equal to the mole fraction times the vapor pressure of water at the ordinary room temperature, and that is 23.8 torr available from a table. So my new vapor pressure is equal to 19.6 torr. I have lowered the vapor pressure by a small fraction, but enough that I can determine that salt water will evaporate more slowly than pure water will, because its vapor pressure has been lowered owing to the colligative properties of sodium chloride. The final property that depends only on the concentration of dissolved solute particles is osmotic pressure, most famous for its role in plant nutrient uptake. But osmotic pressure plays roles in many other biological processes as well. Now, to understand how osmotic pressure works, consider just how small water molecules really are. Even as molecules and ions go, water molecules are among the tiniest around. So it's possible, and nature does this quite often, to produce a membrane with pores so tiny that only water can get through. Any solutes dissolved in the water are unable to pass through. Now, stop and think about what you might expect to happen if you placed 2 solutions of different concentrations in the same container, but separated them with such a membrane. What do your instincts tell you might happen? Hopefully, our earlier discussions have got you thinking in terms of thermodynamics, specifically in terms of the power of nature's tendency toward higher entropy. Those 2 solutions really want to be of the same concentration to maximize the number of microstates that that system can access. But to accomplish this would mean mixing them, and this can't happen because of the membrane. But there is something the solution can do. Some of the water from the lower concentration, or hypotonic side, can migrate across the membrane to the stronger or hypertonic side. When this happens, there's an imbalance in the masses on each side of the container, which corresponds to a certain pressure. If I could push down on the more concentrated or hypertonic side hard enough to resist flow in from the less concentrated or hypotonic side, that is the osmotic pressure of the system. When one of the two solutions is pure water, it can be calculated using a very simple equation. The equation that governs osmotic pressure looks something like this. It's stunningly similar to something we've seen before, isn't it? It reminds me of the ideal gas law. But it does still contain a Van Hoff factor because it is a colligative property. And in this case, I've moved volume to the other side of the equation to isolate pressure, which I've indicated as pi. This is our indication that it's an osmotic pressure we're dealing with. So let's use this equation and our understanding of colligative properties to answer this question. Seawater has a lot of things dissolved in it, but let's assume that seawater is a 1/2 molar solution of sodium chloride. And I'd like to know what the osmotic pressure is that's exerted when seawater and pure water are placed on opposite sides of a semi-permeable membrane. Now, for starters, I'm going to manipulate my equation just a little bit and acknowledge that number of moles divided by volume is simply the molarity. So we're back into units of molarity now. Now, let's say that we want to run this equation. Well, I'm going to use molarity instead of N and V because that's just more convenient for me. The osmotic pressure, then, is equal to the Van Hoff factor, which we're estimating is 2.0. The molarity, which we've already been given in the problem, 0.5 molar solution of NaCl. We're going to use the ideal gas constant in units of liter atmospheres per mole Kelvin to be sure that we get an answer that we can use in units of pressure. And finally, the temperature at which we would like to know that osmotic pressure. Here we're going to go with 298 kelvins. When I do my unit analysis, I see that moles cancel, liters cancel, kelvins cancel. My only remaining unit is atmospheres, a unit of pressure. So this will give me a correct value. A value of 24.5 atmospheres. That's a pretty significant amount of force pushing, all simply because of osmotic pressure, because of a semi-permeable membrane separating solutions of two concentrations. Now let me demonstrate just how much force osmotic pressure can generate using a simple demonstration that you can do right at home. Osmotic pressure isn't just a fascinating phenomenon. It's also a two-way street. And you can demonstrate this to yourself right at home in your own kitchen using a few things that you've probably already got. You're going to need some raw eggs, a few containers to soak those in, a little bit of light corn syrup, and just an ordinary 5% solution of distilled white vinegar. Now, I'm going to begin this demonstration by removing the shell of an egg, but I'm going to do this chemically. Obviously, peeling a raw egg would be a messy proposition. But my goal here is not to completely expose the insides of the egg. Instead, I want to remove the hard outer shell, leaving behind the semi-permeable membrane, so that I can transmit solutions back and forth, or solvents back and forth across that membrane. So to do this, I'm just going to very carefully and gently place the intact egg inside of my container. And before I go any farther, put my eye protection on because I don't want vinegar in my eyes. And just to be extra safe, I'm going to put on some safety gloves as well. And this is because later I'll be actually handling these eggs so that I can show you what they look like at the end of the process. So let me begin by adding a nice healthy dose of my vinegar solution to the egg. Yeah, enough to submerge it. And in a few moments, we'll notice some bubbles beginning to form on the outer shell. Those bubbles are the byproduct of the acid-base reaction that's dissolving the calcium carbonate in the outer shell. And after a few days of this, we'll actually have an egg where the outer shell has been removed, but that inner membrane is still intact. In fact, here are my bubbles now. You can see the reaction beginning. So after a few days, I expect that shell that's been dissolving in my newly submerged egg in the vinegar solution to look more like this. The shell is completely gone. It's been dissolved into that solution. And you can probably notice a couple of things here. First of all, that the color's changed because the brown shell is now completely gone. But you may also notice that there's a difference in size. We're going to get to that in just a second. But if I were to fish this egg out and give it a little rinse, it would look something like this. So this is the way an egg looks when its outer shell has been removed by dissolving it in vinegar. Now you notice that the membrane is soft. Want to be very careful about how much pressure I apply because it's not indestructible. But what's really remarkable about these membranes is that they are semi-permeable. They're capable of allowing water to pass back and forth across them, but they don't allow most common solutes, things like sugars and ordinary salts. And so they're a perfect way to demonstrate osmotic pressure. And I'm going to do that first by taking this relatively swollen egg here that I've removed the shell from, and after having rinsed it already, I'm going to place it in a fresh container. Now, if what we had determined previously about osmotic pressure is true, I can draw some or most of the water out of this egg if I submerge it in an adequately concentrated solution. But the inside of an egg is already a fairly concentrated solution, so I need to choose carefully. And one of the most concentrated solutions in your kitchen is light corn syrup. This is a very, very thick solution of sugars in water. So if I were to place this around the outside of my egg, I anticipate that the water inside the egg will begin to move across the semi-permeable membrane into the sugar solution. So let's see if that happens. Now, in order to test this, I'll have to open my corn syrup. And I'm going to pour that directly over the egg until it's submerged. Okay. Now, having the egg in contact with my corn syrup allows the water to be drawn out. And if the osmotic pressure concepts we've discussed are true, we should see a very different looking egg when this process is complete. So, let's recap real quickly what we've done so far. We've taken raw eggs, placed them in a vinegar solution. That vinegar solution has dissolved away the outer shell, leaving the inner membrane intact. At that point, we rinsed them and added our corn syrup solution. So now there's a very hypertonic solution, meaning very concentrated around the egg. And after a few days, this is what we get. Looks drastically different, doesn't it? The solution of corn syrup has drawn almost all the water out of the egg. And if I'm very careful, I should be able to retrieve it from the solution. So we can really see what we've managed to do to it. Almost no water left in the egg. But remember, we said that osmotic pressure is a two-way street. That means if I apply a hypotonic solution, something that's less concentrated than what's inside the egg, I should be able to get the water to go right back in and reinflate my egg with water. I'm going to do that using distilled water. So we'll just pour a little distilled water over it and set that aside. And after just a few days, this will be our product. We will have added water back to the egg across the semi-permeable membrane, causing it to swell back to its original condition. So in doing this, we can use some very simple ingredients to very clearly demonstrate how osmotic pressure works. When we place our egg into a hypertonic solution, it shrinks because water is moving out across the membrane. When we place it in a hypotonic solution like distilled water, it draws the water back in and becomes pressurized and reinflates. And now we get to have a little bit of fun with our product and demonstrate just how much pressure really can be built up in this way. Now let's see if we can release the pressure from this egg that we've had sitting in the distilled water. It's an impressive amount of force, isn't it? And it's not just a neat trick like our egg stunt. Osmotic pressure is responsible for the rigidity of cell walls in plants, holding stems and leaves in place. Without it, the cells become pliable, wilting occurs. Different species of fish have evolved to cope with the varying salinity of oceans and freshwater lakes and streams. Oceanic species have to cope with the loss of water to their surroundings, which freshwater fish actually drink through their cell walls as the more dilute water around them works its way back in. Switch their environments, and neither one of them stands very much chance of surviving. So let's summarize this lesson. We started by pointing out how remarkably varied the uses are for rock salt, even though it's a very simple, abundant, and safe chemical. We saw why sodium chloride is used in so many applications, because certain properties of solutions can be altered by dissolving whatever we choose in them. These properties are called colligative properties. The properties depend on overall concentration of dissolved particles in the solution, requiring us to treat non-electrolyte and electrolyte solutes somewhat differently. We saw how the dissociation of electrolytes needs to be accounted for using the Van't Hoff factor, which is estimated using the stoichiometry of the dissociation process. We saw how freezing points can be depressed using colligative properties, and boiling points also can be elevated. We then made a logical extension from boiling point elevation to vapor pressure depression using a new concentration unit, the mole fraction. Using this unit, we can determine how the presence of a solute will affect the vapor pressure of a solution at any given temperature. And finally, we covered osmotic pressure, a natural force which occurs when only the solvent can pass across a membrane to diminish a concentration gradient. This phenomenon gives trees rigidity and makes saltwater and freshwater fish biology so drastically different. From expressing concentrations to solubility and saturation to colligative properties, we've only scratched the surface of how chemists create and use solutions. We'll see many more examples of solutions as we move forward. But for now, it's time to move on to a new topic. Our next lecture will kick off a series on a very different kind of consideration: the speed of chemical reactions.